In Chapter 5, we'll have 3 parts, and this is because atmospheric circulations require understanding of a number of forces. Specifically, the pressure gradient, Coriolis, and frictional forces will be our focus for this lecture. How pressure gradient and Coriolis forces balance to make something called geostrophic balance and geostrophic winds. And then finally, we'll look at how friction changes that wind force balance. The pressure gradient force is pretty simple to follow. Winds start as air gets pushed from high to low pressure. So at some constant elevation in the atmosphere, if there's higher pressure in some location, wind will develop and try to go from high to low pressure. The sharper the change in pressure, as shown when isobars, which are lines of constant pressure, are closer, means that the pressure is changing more over distance. In other words, the pressure gradient gets stronger as the isobars are packed together more tightly. The pressure gradient force is often responsible to initiate motion, but you also have to understand Coriolis and friction forces and how they're going to sway the ultimate movement of the wind.
Coriolis effect. An object in motion appears to be deflected from its course, as if a force is pulling it sideways. To demonstrate this point, let's imagine a game of catch being played by 2 people on a merry-go-round that spins like the Earth but is flat. Without rotation, the ball appears to follow a straight path from thrower to catcher. Imagine the ball is tossed from the center to someone at the edge. With rotation, the ball still travels in a straight line in space, but because the catcher is moving, the ball misses. From the vantage point of the catcher, the ball appears to curve away. The direction of apparent motion is to the right when following the path of the ball. Now the ball is thrown the other way. Because the thrower is moving, the ball has a velocity component to the right. The motion of the ball appears deflected to the right, and the ball misses the catcher again. Let's look at a throw across the merry-go-round. Both people move with the merry-go-round. The ball is thrown. Although it flies straight, it appears to be deflected from its original path. Apparent deflection increases as the ball travels farther. In the southern hemisphere, rotation is clockwise when viewed from over the pole. Again, the ball follows a straight course, but its apparent flight path is diverted. This time, the effect is to divert the motion to the left. On Earth, all free-moving objects, including masses of air, are subject to the Coriolis effect. In the northern hemisphere, objects are diverted to the right, as viewed from the direction of original movement. In the southern hemisphere, the deflection is to the left.
So that short video gives us some guidance on if we were on a rotating disk, but the reality is we're on a rotating sphere, so the Coriolis force actually changes with latitude. The Coriolis force is really due to 2 laws, the conservation of angular momentum and the effects of what's called the centrifugal force. The conservation of angular momentum states that angular momentum must be conserved, and here it is as the product of mass times tangential velocity, which for this figure skater is the velocity of her fingertips as she's spinning around, and the radial distance from the axis, as measured from her axis of rotation out to her fingertips. When a figure skater tucks her arms in, the radius decreases. In order to conserve angular momentum, this means that her velocity, her tangential velocity, must increase accordingly to conserve that angular momentum. On the Earth, it works in a similar way. R here is the radial distance from the axis of rotation of Earth, and it's at a maximum at the equator, going down to a minimum at the polar regions. So for an object at the equator that's rotating around with the Earth, as it tries to move to the north, it's moving from an area where the radius is larger to an area where the radius is smaller. As a result, its tangential velocity must increase, which in this case moves it to the east, moving faster than stationary objects on the surface of the Earth at that specific latitude. So to conserve angular momentum, again, an object heading north from the equator gets accelerated to its right in the northern hemisphere, In other words, it gets turned towards the east. So this works just the opposite way for an object that starts in the higher latitudes with a small radial distance from the axis of rotation. As it tries to move to its south to an area with a larger radial distance, it has to reduce its tangential velocity, which means it's going to be rotating against Earth's rotation. In other words, it appears to get deflected towards the west. Again, the object turned to its right. So an object heading south in the northern hemisphere gets accelerated to its right, which means it gets turned towards the west in this specific scenario. If you look at Earth's curvature, you'll find that the radial distance changes the most at the polar regions up here. Here there's not a whole lot of difference between the distance to the radial axis, so therefore this conservation of angular momentum is somewhat of a weak law here. And then there's stronger changes up here. If you move north even just a little near the poles, you're changing your distance from the rotational axis quite a bit. As a result, you have to change your tangential velocity, which means the Coriolis force increases in strength as you get towards the poles. However, you can also think of moving northward more quickly. That will also change your distance from your radial axis more quickly. So the Coriolis force gets stronger as you get towards the poles, but it also gets stronger the faster you move in a northward direction. Now, the conservation of angular momentum explains why air that's either moving north or moving south gets deflected, but it does not explain why air moving zonally, which means either east or west, also gets deflected to its right in the northern hemisphere. Air that's moving east or west along a constant latitude line isn't changing its distance from the axis of rotation, so it's not conservation of angular momentum that makes this air get deflected to its right. Instead, what it is called centrifugal force, and this is the force that wants to throw you away from a spinning axis like on a merry-go-round. Somebody pushes you around on a merry-go-round, there is a centrifugal force that wants to throw you off that merry-go-round. Alright, so those guys proved what centrifugal force is. For the Earth, everybody's rotating with the planet, even stationary objects, so there's a centrifugal force on anything on the planet. However, we have a term called effective gravity, which accounts for that extra centrifugal force, which works against true gravity, and adding those two forces together, we come up with something called effective gravity, which accounts for that little bit of centrifugal force that even stationary objects have. However, for air moving west to east, it's moving faster and has stronger rotation than the actual planet does. So there's an additional stronger centrifugal force on objects moving west to east. And alternatively, objects moving east to west against the planet's rotation have smaller amounts of centrifugal force exerted on them than even stationary objects. Here this graph is showing this. An object here that's moving zonally, in this case west to east means into the screen, we're going to have a centrifugal force trying to push it off the planet in the directions shown as F subfugal here. This has two components if you break it into components, just like you could break a northwest wind into a north and a west component. Here we're breaking down this centrifugal force, which is away from the axis of rotation, into a force normal to the surface of the planet, upwards, and then tangential to the planet, downwards towards the equator. So any object that has a west to east movement over the surface of the Earth has a centrifugal force moving out away from the axis of rotation, which gives you a component of that force to try to turn it to its right, towards the equator. Alternatively, air going in a westward direction, from east to west, has a net centrifugal force moving in towards the rotational radius. To get a sense of this, if you're on a fast-moving merry-go-round and you could actually walk up against the rotation of that merry-go-round, you would have less centrifugal force trying to throw you off that merry-go-round if you were able to do that. So for this graph, an object moving east to west would be coming up out of the screen at you at this point right here. That would be what an object going east to west would look like in this scenario. In that case, there's a net centrifugal force pushing it towards the axis of rotation. Again, simply less centrifugal force than a stationary object, so it must be having a force going in towards the axis of rotation, and that has components going downwards towards the center of the Earth and also upwards towards the pole. If I take that component that goes upwards and put it on the surface of the Earth, you can clearly see that an object that started initially going east to west now gets deflected to the north, again to its right. In both cases, the objects moving either west to east or east to west were deflected to their right, which is in line with the effect we saw for objects moving south to north or north to south. Now, as shown in this graph, there are vertical components to the centrifugal force trying to throw objects that are moving west to east up into the air and objects that are moving east to west down into the earth. However, those forces are quite weak in comparison to the dominant forces in the vertical, which are the vertical pressure gradient. There's a strong change in pressure as you go up in the atmosphere. For example, in Boulder, we're at about 840 millibars of pressure. As you go up to Long's Peak, you're at like 600 millibars of pressure. So a strong vertical pressure gradient is always almost balanced by the gravitational force pushing down towards the planet. Those forces are so strong that this weak vertical component of the centrifugal force really doesn't matter as far as the vertical balance budget. However, the horizontal parts of the centrifugal force are very important because other forces are equally weak in a horizontal force balance. This graph's just trying to show that even for west to east moving wind, that centrifugal force gets stronger as you increase the winds or as you get towards the poles. They're trying to show a constant latitude line has curvature around here, and therefore if you're trying to go in a straight line, you overshoot that and end up getting curved towards the equator. So again, Coriolis turns it to the right in the northern hemisphere. They're showing a weak wind, dashed here, gets turned a little bit, and then a strong wind gets forced even further to the south. So strong winds get more Coriolis force exerted on them than weak winds. So quite a bit of information there, but it's nice to know where the Coriolis force comes from. It's a function of both the conservation of angular momentum, which takes an effect of wind going either north or south, and the centrifugal force, which takes effect for winds going zonally. The important facts about the Coriolis force: the Coriolis force causes moving objects to turn to their right in the northern hemisphere and to the left in the southern hemisphere. The Coriolis force cannot initiate motion, however, it can change the direction of motion. The Coriolis force increases as an object's speed increases, and the Coriolis force is zero for stationary objects. So an object needs to be in motion for the Coriolis force to take effect. The Coriolis force is exactly zero right at the equator and increases to a maximum magnitude at either poles. The Coriolis force is most important for air movement over large distances and becomes insignificant for very small scale circulations, for example, dust devils, even small tornadoes, or toilet bowl motion. Given what we've just learned, what would we expect for the trajectory of an air parcel at the equator if we give it a single small push towards the North Pole? In other words, we're going to force it to move to the north, but then not put any additional force on it, but it's going to be on a rotating planet. Would it be A, B, or C? Now, if we look at choice A, it might make sense initially because you know that objects will get turned to their right in the northern hemisphere, but it should be turned to the right always for all time. And we're saying this object's eternally in motion, so it cannot keep going in a straight line because Coriolis is always going to try to turn it to its right. Okay, so now we can look at point B here, and this makes more sense in the northern hemisphere because it continually turns the object, the air parcel, to its right as it goes around. But as it crosses the equator, it doesn't make sense because objects in motion get turned to the left in the southern hemisphere, and this one's clearly getting turned to the right. C, however, clearly makes sense here. As it goes towards the north, it gets deflected to the right. Now it's moving zonally, it gets deflected to its right. It crosses the equator where the Coriolis forces switch signs and turn things to their left. Crosses the equator again, gets turned to its right. So this object would end up making a wave as shown along the equator. That one's pretty tricky, okay? But here's what you'd expect away from the equator in the northern hemisphere and southern hemisphere. An object that's pushed in motion and left in motion will continually turn to its right due to Coriolis, and an object in the southern hemisphere that's put in motion will continually turn to its left. Here we have to consider a balance between the pressure gradient force, because there's always pressure gradients in the atmosphere, and the Coriolis force. Here we're starting with a pressure gradient Pressure is decreasing to the north, 500 millibars decreasing to 495 millibars, so there's a pressure gradient force trying to push it from high to low. Initially the object's stationary, and then it acts under the force and gets pushed to the north. As that wind speed develops, Coriolis force, which is a function of wind speed, will get stronger and stronger as the wind gets stronger. So in A, again, stationary, no Coriolis force. In B, it has a little bit of wind heading towards the north. Therefore, Coriolis tries to turn it a little bit to its right. As it accelerates even more, because the pressure gradient force is going to continually try to accelerate to the north, Coriolis force gets stronger as the wind speed gets stronger and turns it to its right even more. At point D here, pressure gradient force again is still just as strong as it was, trying to push it from south to north. Coriolis force is now getting stronger because the wind has now accelerated to such a point that it has a wind speed strong enough that the Coriolis force is almost as strong as the pressure gradient force. And finally, at point E, now the wind has reached some critical velocity where the Coriolis force can be strong enough to exactly oppose the pressure gradient force. So in the process of this spin up, there was an acceleration from south to north, but eventually the wind got strong enough that the Coriolis force, which is a function of wind speed, got strong enough to work against the pressure gradient force. And what you're left with is no further acceleration. There's a balance of forces, but instead you're left with a constant wind speed. This wind speed is called the geostrophic wind, and the wind direction is part of that too. So the geostrophic wind is the wind that results from a perfect balance between the pressure gradient force and the Coriolis force. In the northern hemisphere, you will always have high pressure to the right of the geostrophic wind direction. I find it useful to always think if there's a pressure gradient force going from south to north, it's going to accelerate wind to the north, but Coriolis is going to turn it 90 degrees to its right, and the resulting geostrophic wind will go parallel to the isobars and not across them. So again, once balanced, the result is a wind speed with no further acceleration, a constant wind speed going parallel to the isobars. These geostrophic winds only exist without friction, so you get closer to geostrophic winds in the mid to upper atmosphere when there's less friction involved. Near the surface, friction has a say. Now here's looking at what happens when you introduce friction to that balance. So now we're going to consider frictional forces balancing pressure gradient forces as well as Coriolis forces, a three-way balance between them. So if we're near the surface, we have to consider friction, and here's what it does to the wind. Friction always opposes the wind. In other words, it's a force that tries to slow down the wind, which is why the friction vector here is pointed in the opposite direction of the wind. The pressure gradient force, again, is always going to point high to low. So it's pointing high to low in this scenario. The Coriolis force is always in the northern hemisphere, directed to the right of the wind. So what we can see here is if we did not have friction, this Coriolis force would exactly oppose the pressure gradient force, and the wind would go straight down the isobars. But with friction, it slowed down the wind. And by slowing down the wind, that weakened the Coriolis force, which again is a function of wind speed. You weaken the wind speed, you weaken the Coriolis force. So friction did that to the wind. And that means the Coriolis force gets weaker than the pressure gradient force, allowing the pressure gradient force to push the wind slightly from high to low pressure, which is what it's always trying to do. Here we can consider a scenario with a south-moving geostrophic wind, again a perfect balance between pressure gradient force and Coriolis force, that interacts with friction when it hits turbulence over the west coast mountains, say the Cascade Mountains. Which way will the wind turn when it interacts with this friction? So the first thing you have to do is understand where the high and low pressure must be for this geostrophic wind to be heading south. So in the northern hemisphere, again, the way I think of it is, if there was a pressure gradient aligned here, a parcel would initially try to go from high to low, and Coriolis would turn it to its right, and it would end up going down in between the high and low along isobars. So in this case, pressure gradient force always from high to low. In geostrophic balance, the Coriolis force counteracts that pressure gradient force, and in this case, you end up with a south-moving geostrophic wind. So once you encounter friction, it's going to slow down the wind, it's going to weaken the Coriolis force in comparison to the pressure gradient force, and it's going to turn the wind towards low pressure. So in this case, the wind's coming from north to south. If you're looking down with the wind coming down to California, it gets turned towards the left, towards low pressure again. The resulting force balance is the pressure gradient force hasn't changed, it's still going from high to low. The Coriolis force has gotten smaller, but it's also changed its orientation because it's always to the right of the wind flow, and the frictional force is against the direction of the wind, trying to slow it down. Without friction, like this upper level map, wind tends to move along isobars, as suggested earlier in this discussion, or in this case along lines of constant height. For a constant pressure surface, this one the 500 millibar surface, you do have different heights of that surface, which is something we'll get into in future lectures. For the point now is that these wind vectors, which are showing winds here blowing from the northwest, here again blowing from the northwest, and here blowing from the southwest, they follow pretty well those lines of constant height. And we'll find later on that that's very similar to lines of constant pressure. The true geostrophic winds follow isobars, or lines of constant height. With friction, however, here's at the surface, the wind tends to blow towards low pressure, so into low pressure systems and out of high pressure systems. So here, the wind shown, the direction here for this wind station model is coming from the north, this direction. This one, it's coming from the northeast, so it's blowing kind of along the isobars, but also crossing from high to low. And that's a result of friction, allowing the wind to evacuate high pressure systems at the surface, go from high to low slightly, and allowing the wind to push into low pressure systems at the surface, allowing them to rotate around, but also into the low pressure system. That's again a result of friction. Key points for this section before you get some practice with a number of exercises. Geostrophic winds are a balance between pressure gradient force and the Coriolis force, and they blow parallel to isobars. In the northern hemisphere, the geostrophic winds will have high pressure to their right. In the southern hemisphere, the geostrophic winds will have high pressure to their left. Friction makes the winds veer towards low pressure. If you introduce more friction, the winds will turn towards low pressure even more. This effect ultimately helps mix up pressure and temperature anomalies pretty well, which is a function we'll look at later in this class.